When you raise your head to the night sky, what do you see? Countless stars, each a potential sun, perhaps silent witnesses to worlds orbiting around them. Humanity, since the dawn of its existence, has gazed into this endless darkness and asked the same fundamental question: are we alone? This question propelled us to cross oceans, discover continents, and ultimately break free from the gravitational chains of our own planet to set foot on the moon. But what if the true discovery isn't those cold star systems out there, but reality itself? What if this vast, magnificent universe we inhabit is merely a single drop of water in an infinite ocean? This is no longer just a poet's dream or a philosopher's thought experiment. This is the very forefront of physics today. The equations written on blackboards, the clues sought in massive particle accelerators, and the deepest question that keeps the brightest minds awake at night. In this video, we'll break down the walls of the reality you know, putting on the table the possibility that your what-ifs and maybes could be tangible worlds. We invite you to a garden where every step you take creates a new universe, where infinite paths diverge. Fasten your seatbelts, because this journey will take you not only to the farthest reaches of the cosmos, but also to the heart of existence's most fundamental questions. Welcome to the Symphony of Multiverses. Think about that moment in your life when you came to a crossroads. That job offer you didn't accept. That person you dared not speak to. That path you didn't take. In a corner of your mind, a ghost lives, wondering what kind of life you'd have lived if you'd made a different decision. It's as if another you is living that life you didn't, experiencing joys you didn't taste, suffering pains you didn't endure. Is this just a fantasy, or is it a door opening to one of existence's deepest secrets? What if we told you that these what-ifs, these maybes, these ghost lives are not fiction at all, but that each of them is as tangible and real as your current reality? What if we told you that with every step you take, every decision you make, the universe itself comes to a crossroads and branches into an infinite number of worlds where all possibilities are lived out? This is no longer just a question for poets and philosophers, but for the boldest minds in modern physics. This is a question that leads us to an astonishing cosmic labyrinth we call the Garden of Forking Paths. This journey requires imagination. As Albert Einstein said, imagination is more important than knowledge, for knowledge is limited, whereas imagination embraces the entire world. What distinguishes the human mind from others is its capacity to roam in horizons that have never existed, to conceive the unseen. This video will do just that. We'll start with a personal and philosophical question, what if? And then explore how this question, in the hands of physicists, transformed into a map of the ultimate nature of reality. We'll delve into the depths of scientific theories that stretch from the smallest vibrations of the quantum world to the most magnificent structures of the cosmos, suggesting that our universe is not alone, but perhaps just one melody in a vast symphony of multiverses composed of infinite notes. Fasten your seatbelts, because reality can be much stranger, much grander, and much more magnificent than you can imagine.
We begin our journey by descending into the most fundamental fabric of reality, the invisible realm where everything originates, the quantum world. Here, there are no solid, definite objects as we know them. Instead, consider a fundamental particle like an electron. It's not a tiny ball sitting at a specific point, it's almost a cloud of potential, a wave of probability existing simultaneously here, there, and everywhere it could possibly be. Physicists call this ghostly state superposition. The particle lives out all its possible fates at once until we observe it. This is where physics' most famous thought experiment enters the stage, the double-slit experiment. Imagine sending this electron, in its probabilistic wave state, towards a barrier with two thin slits. According to the long-accepted theory known as the Copenhagen interpretation, the moment we try to detect which slit the electron passed through, that magical wave of probability collapses, forcing the electron to choose a single reality. It either goes through slit A or slit B. All other possibilities instantly vanish. But what happens to those vanished possibilities? Does the universe so easily discard its potentials? However, in the 1950s, a young PhD student at Princeton University, Hugh Everett III, asked a daring question. What if the wave function never collapses? Everett believed that the idea of collapse was an unnecessary patch added later to the elegant mathematics of quantum mechanics. His revolutionary idea was the relative state formulation, later known as the many worlds interpretation, MWI. According to this interpretation, at the moment of an observation or interaction, possibilities don't vanish, reality itself splits and branches like the trunk of a tree. Let's make the analogy clearer. As the electron approaches the two slits, the universe itself splits into two. In one universe, you observe the electron passing through slit A. At that very moment, completely unaware of you, a parallel universe forms with an exact copy of you, and in that universe, you observe the electron passing through slit B. Both outcomes occur. Both worlds are equally real. This splitting process is called decoherence. From this moment on, the two worlds cannot interact with each other, nor can they be aware of each other's existence. They are now two separate branches born from the same root, but reaching for different skies. This idea elegantly solves physics' most famous paradox, Schrödinger's cat. Inside the box, there's a cat along with a vial of poison linked to a radioactive atom. There's a 50% chance the atom will decay within an hour. According to the Copenhagen interpretation, until the box is opened, the cat is in a superposition of being both alive and dead. The many worlds interpretation, however, clarifies this blurry picture. There is no paradox. At the moment of interaction, the universe has branched. In one branch, the atom has not decayed, the cat has survived, and the observer opening the box is happy. In the other branch, the atom has decayed, the poison has been released, the cat has died, and the observer experiences great sadness. Both scenarios are absolute realities in their own universe. Both observers are right in their own reality. Now, let's bring this idea back to the beginning, to your personal crossroads. Every decision you make, even a quantum event at the most fundamental level, like a neuron firing in your brain, according to the many worlds interpretation, means there's a universe where you accepted that job offer. There's another universe where you talked to that person. There are infinitely many yous who walked that path you didn't, living completely different lives. According to this theory, the universe is like a gigantic tree that branches into an infinite number of possibilities every moment, every second, with every quantum whisper, and we are merely travelers on one of these branches. The most striking aspect of this interpretation, despite the abundance of universes it presents, is that it actually simplifies the theory. It removes that mysterious collapse rule from quantum mechanics and states that only a single fundamental equation, the Schrödinger equation, is valid always and everywhere. Perhaps the simplest mathematical path leads us to the most incredible conclusion. Reality is not a single story, but a vast library where infinite volumes are being written simultaneously.
Now, let's move away from those intimate and personal branching quantum realms and turn our lens to the largest conceivable scale, the universe itself. Let's start with the story we all know. Approximately 13.8 billion years ago, the entire universe was born from a single point of infinite density in a magnificent explosion, the Big Bang. This is our standard model for the beginning of the cosmos. However, as successful as this model is, it contains some annoying questions.
For example, why were different regions of the universe so similar in temperature and uniformity, despite not having had time to interact with each other? This was known as the horizon problem. In the 1980s, physicist Alan Guth proposed an ingenious solution to these problems: cosmic inflation. According to this theory, in an incredibly tiny fraction of the first second after the Big Bang, our universe expanded at a dizzying rate, much faster than the speed of light. An area smaller than a subatomic particle suddenly became larger than the observable universe. This sudden and massive expansion ironed out all the bumps and irregularities from the beginning of the universe. Like a balloon being inflated smooths out wrinkles on its surface, creating the incredible uniformity we observe today. However, this revolutionary idea had an even more unsettling consequence. When physicists like Andrei Linde and Alexander Vilenkin investigated this inflation process more deeply, they realized that once inflation began, it didn't necessarily have to stop everywhere at the same time. This was the birth of the theory of eternal inflation, or chaotic inflation. To visualize this theory, let's use the analogy of: imagine all of existence as an endlessly expanding, boiling ocean of energy. This is a meta-universe, or a cosmic foam. Within this bubbling ocean, some regions randomly stop inflating and cool down, becoming stable within themselves. Each of these regions, like bubbles in boiling water, forms a universe on its own. Our known universe, which contains billions of galaxies, is just one of countless bubble universes in this infinite cosmic ocean. The most striking aspect of this model is that each bubble can have its own physical reality. Since the inflation process ends differently in each bubble, the fundamental physical constants of each universe, like the gravitational force, the mass of an electron, etc., can differ from each other. In one universe, gravity might be much stronger, while in another, completely different fundamental particles might exist. This paints a picture of a hierarchical multiverse, composed of universes that come together at different cosmological scales. This theory dethrones the Big Bang. It is no longer the sole beginning of everything, it is merely the moment when our local bubble stopped inflating and began its own cosmic life. Just as the Copernican revolution removed Earth from the center of the universe, the theory of eternal inflation transforms our Big Bang into one of countless events in an infinite ocean of creation. And traveling between these bubble universes is impossible, because the space between them is still expanding faster than light. They are eternally isolated from each other. They are parallel worlds floating in the same cosmic sea, but never able to reach each other. We are residents of a calm island in this endless sea of foam, unaware of the existence of countless other islands beyond our horizon that we cannot even imagine. Now, we've arrived at the deepest and perhaps most dizzying stop on our journey. We're turning our lens from the largest structures of the universe to the smallest, most fundamental components of reality, the Planck scale. At this scale, where an atomic nucleus remains as large as a galaxy, the very concept of a particle as we know it loses its meaning. Here we encounter modern physics' most elegant and controversial idea: string theory. According to this theory, the fundamental building blocks of the universe are not point-like particles, but one-dimensional, continuously vibrating loops of energy, strings. The beauty of this idea lies in the unifying power it offers. Just as a violin string vibrates in different ways to produce different musical notes, these fundamental strings, by vibrating at different frequencies and modes, give rise to all the different particles and forces in nature. One vibrational mode creates an electron, another a photon, and yet another a graviton, which carries gravity. This is a candidate for an ultimate theory of everything, promising to unite the two giant theories of physics, quantum mechanics and general relativity, under one roof. However, for this magnificent symphony to be played, the mathematics of the theory demands that we accept something radical.
Our universe is not limited to the 3 spatial and 1 time dimension we know. For strings to vibrate freely, the universe must have 10 or 11 dimensions. So, where are these extra dimensions? According to the theory, these extra dimensions are compactified, meaning they are curled up so small within themselves like a bud that we can never directly perceive them. This multidimensional framework is known as M-theory, which unifies all string theories. This is where the idea of multiverses appears in its most spectacular form. According to M-theory, our 4-dimensional universe is nothing more than a giant brain, short from membrane, floating in this higher dimensional hyperspace, referred to as bulk in English. To visualize this structure, the slice of bread analogy is used. The multiverse is a loaf of sliced bread. Each slice is a parallel brain containing an entire universe within itself. These universes, like stacked sheets of paper, are parallel but different realities. Perhaps the most unsettling consequence of this model is the entirely new explanation it provides for the Big Bang. According to this scenario, known as the ekperiodic universe or cyclic model, our Big Bang was not a singular beginning born out of nothingness. It was the result of 2 parallel brain universes floating in this higher dimensional space, catastrophically colliding with each other. The immense kinetic energy of this cosmic collision was converted into the sea of matter and energy that formed our universe and triggered its expansion. This could be part of a cycle lasting trillions of years. Brains collide, universes are born, expand, cool, and eventually collide again, initiating a new cycle. String theory is one of the most ambitious and mathematically beautiful structures created by the human mind. However, this elegance comes at a cost. The theory is built on concepts that are almost impossible to prove. Strings at the Planck scale are too small to be directly observed. We have no evidence for the existence of extra dimensions, and the energy levels required to test the theory are far beyond our current technology. Therefore, some critics argue that string theory is more of a mathematical philosophy or metaphysics than science. Yet it continues to be the most comprehensive and promising dream about the deepest secrets of the universe, perhaps a dream we will awaken to with new technologies, such as gravitational wave observatories in space.
So far, we've looked at the idea of multiverses through 3 different doors: the infinite branching of quantum mechanics, the bubbles born from cosmic inflation, and the symphony played by strings in hidden dimensions. Each fundamentally shakes everything we know about reality. However, at this point, like an honest inquirer, we must pause and ask the most difficult questions. What if all of this is just mathematical fantasy? Are these theories truly science? At the heart of these questions lies a massive problem, particularly brought forth by string theory, the string theory landscape. The theory doesn't predict a single outcome, like our universe. On the contrary, its equations show at least 10 to the power of 500 different stable solutions, meaning potential universe vacuums with different physical laws. This is like an incredibly vast, multidimensional mountain range, where each valley represents a different universe. This landscape offers a potential answer to one of physics's biggest puzzles, the fine-tuning problem. The question is, why are the fundamental constants in our universe, gravitational force, the value of dark energy, the masses of fundamental particles, etc., so precisely balanced to allow for the emergence of life? If any of these values were slightly different, stars, planets, and thus we, could not exist. The multiverse landscape provides a controversial explanation for this, the anthropic principle. According to this principle, if there are trillions upon trillions of universes, it's not surprising that at least one of them, by chance, has the right conditions for life. The very reason we exist in this universe and can ask this question is precisely because conscious observers capable of asking this question never existed in the other, life-unfriendly universes. This is where we push up against the boundaries of science and where criticism is most intense. For a theory to be considered scientific, one of the most fundamental criteria is that it must be falsifiable. That is, there must be a potential experiment or observation that could prove the theory wrong. According to critics, if a theory predicts every possible universe, then it actually predicts nothing. Whatever observation we make, a universe in the landscape will fit it. This pushes the theory into an untestable and therefore unscientific realm. Many respected physicists reject these theories precisely because of their untestability. Of course, there are strong arguments against these criticisms as well. Proponents of the many worlds interpretation argue that their theory doesn't add anything new, but rather removes an arbitrary assumption from quantum mechanics, the collapse of the wave function, making it simpler and more elegant. They contend that even if other worlds cannot be directly observed, the underlying quantum mechanics equations are tested daily in laboratories. Similarly, some cosmological models, such as colliding brains, are hoped to leave specific imprints in the cosmic microwave background radiation that could be detected, or that future gravitational wave experiments might offer the possibility of testing these theories. The eternal inflation theory, on the other hand, grapples with technical difficulties like the measure problem within itself. If there are infinitely many universes, how can we calculate our probability of being in any one of them? This is a question that pushes the boundaries of statistics and probability. At this point, it will help us grasp the whole picture if we pause for a moment to compare the three major multiverse ideas we've encountered on our journey, understanding their differences and similarities. Each is a theory with its own unique logic and language, reaching the same multiverse destination via different paths. First, let's look at the many worlds interpretation, which arises from the heart of quantum mechanics. This theory is the most personal and intimate. Its core idea is that with every quantum event, the universe splits into an infinite number of copies, like the branches of a tree. The key analogy here is the branching tree, where every decision leads to a new branch. The most striking feature of this model is that the laws of physics remain completely the same in all these branches. Only the outcomes of events change. Scientifically, this is an interpretation, not a new theory. Although we cannot directly observe other worlds, the underlying quantum mechanics equations are tested daily in laboratories. Secondly, there's the theory of eternal inflation, which comes from the largest scale of the cosmos. This is more like a cosmic foam or bubbles in a boiling ocean. Each bubble is a universe completely isolated from us, experiencing its own Big Bang. The most radical aspect of this model is that each bubble universe can have its own unique laws of physics. Our universe's constants are just one of infinite possibilities. This theory is an extension of the Big Bang model, and while it cannot be directly tested, it's thought that some versions of it might leave potential traces in the universe's oldest light, the cosmic microwave background radiation. Finally, we come to the most abstract and ambitious, string and brain cosmology. This theory conceives of reality itself as membranes or slices of bread floating in a much higher dimensional space. Our universe is just one of these slices. In this model, new universes arise from the collisions of these branes, or from different mathematical solutions within the vast landscape predicted by string theory. In this model, too, the laws of physics can be fundamentally different in each brane or each valley of the landscape. Its scientific status is the most speculative. It relies on a purely theoretical framework and is almost impossible to test with our current technology. Although it's hoped that future gravitational wave observatories might offer some clues. These three pictures show us that there isn't a single multiverse idea, but rather a family of competing and complementary ideas. One starting from the smallest scale, another from the largest scale, and yet another from the very dimensions of reality itself, all lead us to the same dizzying conclusion. There may be far more than what we see. Ultimately, the multiverse hypothesis lies at the most exciting and also most controversial frontier of science. It forces us to think deeply, not only about the nature of the universe, but also about what knowledge and science itself truly mean.
As our cosmic journey draws to a close, we return to where we began, ourselves. This dizzying journey, from quantum whispers to colliding universes, not only maps outer space, but also compels us to question the most fundamental concepts of our inner world. If multiverses are real, what does this mean about being me, making choices, and finding meaning? First, let's consider the concept of self and identity. If every alternative of every decision you make happens in a different universe, then who are you? Is it you living a humble life in this universe? Or is it the you in another universe who took that risky step and achieved great success? Or the other you who made a terrible mistake and lost everything? This theory transforms our self from a single coherent narrative into a sum of infinite possibilities. Perhaps the real you is the totality of these infinite copies, and each life is just one facet of that immense whole. This takes the idea that one cannot escape oneself to the extreme. No matter which universe you are in, you are forced to confront a different version of yourself. This brings us directly to the problem of free will. If you inevitably make every choice you can make in a different corner of the multiverse, does this eliminate free will, or does it glorify it in the most absolute way? On one hand, if all outcomes inevitably occur, it might seem meaningless for you to choose a single path. You are merely a puppet drawn towards the branch dictated by the current circumstances. On the other hand, perhaps this is the ultimate triumph of will. Every one of your thoughts, every one of your dreams, every one of your potentials comes true somewhere. The universe takes every one of your possibilities seriously and grants it a world. And finally, we come to the deepest question: cosmic purpose. As the anthropic principle suggests, is our existence merely the lucky outcome of a cosmic lottery? Is the universe fundamentally a meaningless and purposeless mechanism that accidentally brought us into existence after countless attempts? Or does this landscape itself point to a deeper purpose? Perhaps the universe, by its very nature, is a giant learning machine trying to explore consciousness and life in every possible way under every kind of physical law. Perhaps the purpose is not a single outcome, but the very existence of possibilities. Ultimately, even if the multiverse theory is not a proven reality, it is a triumph of human imagination. It is the boldest expression of our urge to understand our place in the universe, to seek answers to the question, why are we here? Just as our ancestors looked up at the night sky and saw stories in the stars, we too are now using the language of mathematics and physics to search for possible stories, alternative realities, in the fabric of the universe.
We have reached the end of our journey. We have stretched from the uncertain whispers of the quantum world to the bubble universes born of eternal inflation and to the mysterious 11-dimensional dance of strings. Each theory pulls the familiar solid ground of reality from beneath our feet, leaving us in a dizzying landscape full of possibilities. So what do all these theories, these incredible ideas, tell us? Perhaps the most important lesson is that the universe is much larger, much stranger, and much more creative than we perceive it to be. Perhaps existence is not a melody composed of a single note, but a vast symphony with infinite instruments playing simultaneously, containing all notes, both harmonious and discordant. Our lives, our universe, are a strong, clear melody in this symphony. But in the background, there are infinitely many other melodies we cannot hear, perhaps will never hear. This idea can make us feel small. It can make us feel like an insignificant speck of dust lost in infinity. But perhaps the opposite is true. Perhaps this shows how valuable every single choice, every single potential truly is. Because every yes or no might trigger the birth of a brand new world, not just our own, somewhere. This excursion to the boundaries of science has left us with bigger questions than definitive answers. And perhaps that's the most beautiful part. Because what makes us human is not finding the answers, but searching for them. The next time you come to a crossroads, pause for a moment. Imagine not just which path you will take, but also that other you who has started walking the path you didn't. That other world, that other possibility. Because perhaps the greatest secret of the universe is ultimately hidden not in an equation, but precisely in that imagination.
The Door to Knowledge, presented by Toyer TV. Don't forget to take your place on this path of discovery and enlightenment.